All right, y'all. Here we go. This is where we left off yesterday. And I did go through all of these, but I want to do kind of a quick reminder. There's two different ways of breaking down and simplifying square roots. One of them is looking for the perfect square that is contained within this. And I think we did this for this middle one, but I wrote it. And I think yesterday my description was it looked like I was holding a crayon in my toes. So, like, if I'm looking for perfect squares that are contained within here as a factor, one of them is 100, and the other of them is 25. And if I look at that, it's 100 times 2, and it's 25 times, I believe we said 8, as we looked at something like that. And so that if we're going to break them down, you're just breaking down the root into two different parts. This is now 10 root 2, and I can't do anything else with that. Or square root of 25 is 5, square root of 8, and then I just have to look and see, can I keep breaking down? And since I can break 8 down into the perfect square 4, this is 4 times 2. We know the square root of 4 is 2, so this is 5 times 2 times the square root of 2, or 10 root 2. So you're going to get the same answer no matter what. But what it comes down to is if you can find the largest perfect square factor that goes into it, you only have to break it down once. If you find a smaller one, you can just keep breaking down until there's nothing else that comes out of the radical sign. Now, with that being said, how many people have any questions about this process, the idea of looking for a perfect square and then breaking it out? If you've got a question, I'd love to know it. If not, that's totally fine too. Just say move on, and then I'll move on because I want to show you the other way as well.
Where does the sign, like the root sign or whatever, go from the first number?
So in this case, when you take the square root of 100 and you simplify it, I know that the square root of 100 is equal to 10. So the root sign itself goes away when you simplify that radical and turn it into just the number that is outside of the radical. So like this root 25 became a 5 and I didn't have a root anymore. But since the 8 didn't break down, I kept it underneath there. It takes finding the perfect square underneath it to then simplify it and take it out. Does that make sense?
Is it possible to do this in reverse? Like, could you go from 10 root 2
Oh, to
to...
put things underneath there? Yeah, if I wanted to, God, this will be fun, I guess. Let's start with, I'll go 7 root 3. Okay. So if I'm going to do that, that's completely and totally fine. If I want this to go back underneath the radical, I'd have to square it. So 7 is the same as the square root of 49. And then if I wanted to put those together as an actual product itself, I'd have to do 49 times 3, which is 100 and, well, let's think, 147, I think. So that'd be square root of 147 because 149 times 3 is that. So this is like doing it in reverse. It's once you've simplified it, you can put it back under the radical when you square it. Does that work for you in terms of the understanding?
Kinda.
Okay. And again, I honestly, we generally don't go in this direction. Like I can't think of an application that I've ever had to use where besides creating problems for like math tests that I've had to do anything like this. But that's the way that one would do that. And that's kind of the way I would look at it. Um, but essentially, it's the only way that you can take a radical and get rid of the root sign at all is to recognize that it's a perfect square and to take it out like this so that we know that 10 and the square root of 100 are equivalent expressions. Or if I have something written down where it's a square root and I've got two different numbers underneath there that are the same. So, like, if underneath here I have, let's go 9 times 9. Now, I know what 9 times 9 is. Do you guys? What's 9 times 9? Somebody write it in the chat. It'll make me feel good about myself. Yeah, 81. So I know that the square root of 81 is 9 because it's just 9 squared. I mean, like, the nice thing is it's right there. So if I took the square root of 81, it would just give me 9. So if I have a pair of factors that are the same underneath the radical sign, I'm saying that what I look at there is in fact something that could be simplified as just the 9. Like, this is the same as this. If you have two factors, it's like saying 9 squared, and a square root and a squared cancel each other out. So it's just this 9. So two ways of simplifying it would be either breaking them down into perfect square factors or pairs of factors. So like here, I was trying to do this over with this one yesterday, but I don't think it was quite as easy to see. So let me show you this with the 28 because I've got a little bit more space over here. If I want to break this down into all the factors I have, like I know 28 is 14 times 2. And then I know 14 can break down into 7 times 2. So underneath here, this is 7 times 2 times 2. When I think about that, I know that I have a pair of factors here. I've got this 2 and 2. And so if I have this in such a way where I've got them split up, there's that root 7 there, and I've got these two 2's here. Anytime I have a pair, this essentially says that those two things can cancel out. And then, sorry, I just read a private message that like made my brain stop mid sentence, and I will say I'm glad that you were here to the person that just wrote that. These two things here will then break each other down and say this is going to be just a 2 outside of the radical sign, and that root 7 stays underneath there. So that'd be my final root for this. And we did that before and found that it was a 4, but it's the same thing when you're finding a pair of factors. So how many of you guys feel like this is an okay review of this, or you'd like to have another one? Because I could definitely come up with a few of these on the top of my head, but I need to get to what we're going to be doing with the Pythagorean theorem. So let me come up with one more if you need it, but if not, we'll just try to do them in the middle of this. Does anybody need another one? If you do, that's fine. Okay, 2 people said that it's okay. If anybody needs it, this is okay here. So I will, when we get to another one, we're definitely going to have to simplify more radicals. So I'll try to go through and make sure that as we're explaining them, we get to both possibilities there. But I think this is sort of where we're going to go. Like the types of problems you're going to see are going to look like this, where you've got part of a right triangle and you need to find the other part. So right now we got 2 pieces. We want to find the third. For me, anytime that we're going to be doing this, our goal is to look for a right angle and then go across from it to identify the hypotenuse, because that is basically going to be our equation. In this case, x is what I'm looking for, right? So I know that x squared is going to be on this side. Then I've got the 2 sides here, 10 and 24. So I'm going to do 10 squared and 24 squared on this side. And so that would mean for this one, what would this equation look like? Could somebody write this in the chat, what this equation would look like if I'm going to set it up using the Pythagorean theorem? This is where I wait patiently, look at the chat. And actually, Ian, what's interesting, the way that you wrote it to solve for the x. I would just write it in the a squared plus b squared part of it, which gets to sort of what Matthew was saying there. And V, you're close, but the one thing you got to remember is it's got to be equal to that 24 squared. So you take the 2 sides here. I normally take the hypotenuse and set it off on the side here first. And then I put the other 2 things over here, square them both, and then square this one, so that when we've got it, it's set up here. And of course, I am going to have to subtract this from this side to get the answer. But these are the sorts of setups that we're looking for. Is you want to have the 2 smaller sides squared, take the sum of those. That's going to be equal to that third side. Okay. Now, for this one, as we're going to be doing this, oh Lord, Veronica, you're right. This is only family things here. Stop quoting your brother. Here's what we're going to do. As I'm going through here, 10 squared is 100. 24 squared is a number that I don't have in the top of my head, but I'm sure that one of you is going to plug it into a calculator for me and tell me what 24 squared is. And that person will be, soon it could be, come on, somebody tell me 24 squared. 576, thank you. So 100 plus 576 equals x squared. This will be 676 is equal to x squared. And then I'm going to take the square root of both sides of this to solve. And this is the place where we could potentially be solving or be simplifying a radical, because here the x squared and the x are going to cancel each other out, and we'll just have, or the x squared and the squared are going to cancel each other out. Lord, trying to do too much at the same time. Square root and the squared will cancel each other out. Then if I take the square root of 676, it is going to give me the final result for this. Now, as I do this right now, I don't in fact know that off the top of my head, but I'm pretty sure this is one that they threw in there as a whole number answer. So I'm going to use one of these myself and say, well, here, let's see what I can do. If I'm going to do this, 676, I get 26 is the final answer for that one. Square root of 676 is 26. So the answer to that one is 26. Now, this next one is going to be interesting. We did just do 24 squared, so we know this is 576. We know 6 squared is 36. And we got x squared here. So if I subtract 36 from both sides, then what I'm going to get is that x squared is going to equal 540. Now, I feel like there's a potential that that is not going to be a perfect square, and I am correct. If I take the square root of both of these things, I'm not going to get a perfect square here. So in the case of this, these will cancel out. It's going to be an x. I got to break down that 540. Now, first off, when we're doing this, the first thing that I would ask you is, do you see any perfect squares that you know go into this right now? Like you look at it, you go, that's a perfect square that goes into that. Tell me if you do. Totally fine if you do. But if you don't, that's fine as well. Anybody see one off the top of your head? And the I'm not sure is probably the right answer, because when you look at 540, it's not set up in such a way that you'd be positive for that. I think 9 does go into that, yes, since 9 goes into 54. So what we can start to do is, if you see them, start to break those things down, because the simpler you can make this number underneath the radical, the easier it's going to be for us to do things with it. And so if I'm doing that, let's go. It is 9 times 60 in this case. So right now, if I break that down, root 9 and root 60, that is now going to give me, what does the root 9 become? 3. So this will be 3 root 60. Now, that 3 is outside. I don't have to do anything else with that besides combining it with other things. That 60 is where I got to focus my time now. What else goes into the 60 that we could potentially use as a perfect square? Can you guys think of anything off the top of your head? Four is probably the number that I would think, because as I look at something like this 60, like there's not any big numbers that go into it. So we start to go with the small ones, and 4 is our first one. It is indeed 4 times 15. Caroline threw that at me in the chat as well. So if I break this down into 4 times 15 and take the square root of those, I still have this 3 on the outside. So I'm going to have 3 here times that square root of 4 becomes a 2, and then I'm going to have a root 15. Now, 15 can only break down into 3 times 5. So this is not going to go anywhere after this. 3 and 2, if I put those together, my final answer for this is 6 square root of 15. And that is going to be my final answer for this third side in simplified radical form. Now, I'm going to tell you, I guarantee you that there is out there on the internet something that you can type in a radical and it's going to simplify it, put it in simplest radical form. I'm going to guess you could type in simplest radical form, and there's a calculator out there that you could just type these numbers into to find them. The great thing for me is that I have a calculator here that kicks them out as well. So I'm looking at this Casio calculator. I typed it in. It actually told me 6 root 15. So I knew that it would simplify and not just give me an answer. And that's helpful for when you're actually instructing people. But it's also something that for you guys, if you're trying to speed up your process of work, if you can get to here, I'd love for you to be able to do this by hand. But I also just want you to recognize, if you see this answer, 6 root 15, you realize that what it means is when I simplify this, there's a part of it that doesn't come out. I don't need us to have a whole lot of work on this, like on stuff like this, but I do want to make sure that you realize that it is a process that we go through. So does everybody feel a little bit better about how we use that with a problem like this? Okay, so here's what I'm going to do. I got a lot of pages to rip through here, and so I'm going to try to go through as much as I can, and we're just going to keep on trucking, okay? Most of what's happening here when we start to look at the Pythagorean theorem, guys, it talks here about another way of using the Pythagorean theorem. Just do me a favor here. If they're asking if something makes a right triangle, in this case, when they give you 3 side lengths, all you have to do is take the 2 smaller ones, take the sum of the squares, and ask the question if it equals the top one squared. It's really easy to check. You square them and add them and get a number. Then you square this, and then you see if they're equal. And if they are, it's a right triangle. And if they are not, guess what? It's not a right triangle. Okay? Now, what I love about this, though, is it takes us to another possibility with what happens there, because there is, in these cases, the possibility that, hey, this will make a right triangle. I'm going to get an answer. But then you've got, remember, we talked about this as a trichotomy. There are 3 possibilities. Either this is equal, in which case, if it is equal, we get a right triangle. Awesome. Or I'm going to have this sum is greater, or I'm going to have that this sum is less than. There are these 3 possibilities. Now, I want you to think about this for a second, okay? If we're looking at this and they're equal to each other, we got a right triangle. What I want you to think about for just a second is When we have done these things within a specific triangle, we realize that the largest angle is opposite the largest side, smallest angle is opposite the smallest side, and then the middle is opposite the middle side. But what I really want us to think about is the comparison here for a minute. Remember when we were using the hinge theorem, if we had two sides that were the same, like let's say this 4 and this 12, then if I'm comparing them, if I'm looking at this opposite side, well, it's either going to be a right triangle, so it's equal to whatever this is, or it's going to be bigger, which means that we're going to be looking at an obtuse triangle because that angle is going to be larger than 90, or it's going to be smaller, which means it's going to be an acute triangle because it's going to be less than 90. Now, how many of you guys understand what the hell I just talked about? Kinda is the right answer here. It's really hard to kind of look at this. I'm going to show this to you in a second. I'll just tell you that if this is greater than the number, it is going to be obtuse. Is that right? Come on, Bechtel, think about this. Actually, it's easier to do it this way. Hey, look, I got a picture here. If the c squared is greater than a squared plus b squared, it's obtuse because this side is longer than it would be if it's 90. If the c side is less than a squared plus b squared, it's acute because this is going to have to be less than 90 for this to be less than the sum there. Now, how are we doing? Okay, I think that this picture helps us because when we're comparing the longest side to the two other sides, it just kind of depends in terms of the fact that if it's equal, it's a right. If this is bigger, it's obtuse. If this is smaller, it's acute. Okay, and I'm glad. Of course, it makes more sense because there's a picture here. That's a lot easier. And so when you're doing this, what you're going to do is you're going to take 8 squared and 10 squared, and you're going to compare that to 16 squared. This is either going to be bigger, smaller, or equal to. 16 squared is equal to 256. This is 100 plus 64. So this is going to be 164. Right now, we know that 164 is less than 256. So would you guys agree that if we're looking at these two things, my C side is now larger than the other two sides? Does that make sense? That the C side is larger than the sum of the squares of the other two sides. So if I look here, if the C side is bigger than that, what type of triangle am I looking at? It's going to have to be an obtuse triangle if this one side, the C side, is larger when I square it than the sum of the other two. Everybody cool? It's easier to take us through this than to try to keep it in our heads. And what we're really doing, my problem with what I was doing above is I was looking at the two smaller sides. The side that matters the most is what's happening with your C side. If C is larger than it, that means it's obtuse because that means it's the longest side and it's bigger than it would be if it was a right triangle. If it's smaller, then that means it's smaller than it would be if it's a right triangle, which would make it acute. Okay, so we are looking at the comparison, and the key is that third and longest side. It's either a hypotenuse or it's bigger or it's smaller. All right, cool. Now, with that being said, let's go to the next thing. Special right triangles. All right, y'all. We are done with the Pythagorean theorem stuff. So you guys have got everything that you need. Yes, stay in school, kids. It'll make you better at PvP. Now, if we're looking at what we're doing here, this is something that actually is kind of important for us to pay attention to. These two triangles, the 45, 45, 90 and the 30, 60, 90, are the ones you'll see the most, okay? They build a lot of stuff on these. There's going to be a lot of things that we're going to be doing later in geometry that are related to these, but you'll actually see these much farther down the road as well when you're starting to deal with trigonometry and all of that. So when we're looking at this, it's important that you understand that what we're really trying to do is make it so that we can find a faster way to do this. Generally, what they'll do with 45, 45, 90s and 30, 60, 90s is they will hope that you recognize the way that all of these are set up. And then they'll give you one piece of information and say the pattern follows, how do you use it? Okay. And so what we're about to do, we got like 8 minutes left in class, which should be enough. We're going to go through and show you how this stuff works and apply it. Now, I've got different examples that we could possibly use when we do this. I can use really easy problems and really difficult problems, and I'm going to try to keep things not overly difficult with the examples for time's sake. But like right here, I want to show you what we got to do for a 45, 45, 90. So here's kind of the way that we go about doing this. Right now, we know that if I've got two angles that are the bases here, if the two base angles are the same, the opposite sides are also equal to each other. That makes this an isosceles right triangle. Is everybody okay so far? So if I got 45, 45, 90, I'm telling you that these two sides have to be the same. That's really all I'm saying right now. Okay. Right now, the reason I'm giving these to you in terms of x is because I want you to think about this as this could be any value. If these were both 7, that would work. If these were both 15, that would work. I know if I have a right angle here and these two sides are equal to each other, then I know that these two base angles have to be the same. Okay? Because if you think about it, if the two sides are the same, if I subtracted from each other, I know the base angles have to be the same. 90 minus 180 minus 90 means I've only got 90 left to split up between the two. They got to be the same. That's why they're 45. That's a lot of words, but we got there. Okay, so what I want to do is show you how we can use the Pythagorean theorem to find out what this third side would be in relation to those two. Is everybody ready? So right now, just for funsies, let's call this one right here. We will call it a big capital C because that's a squared, b squared, and then guess what? That's going to be c squared. So what we're going to do right here, I'm going to say x squared plus x squared is equal to c squared. Now, what I want to do is solve this for c so that we can have it in terms of x. That is really pretty easy, but we haven't done a whole lot of this stuff with algebra recently. So right now, these are both x squared, so we're going to combine like terms and say, I've got 2x squared right here, okay? It's equal to c squared. Now, I would like to solve for c and know what that is in terms of x. So I've got to get rid of this squared to make that work. Getting rid of a squared just means I take a square root of both sides. Now, that should be easy peasy, right? So here, that cancels out, gives me a c. And then I got to worry about this guy. It's actually not bad because if I think about this, this is x squared, right? I know that the square root of x squared is just going to be an x. But I also know that 2 right there, there is nothing that's going to be able to break that down because I don't have 2 of them. That is not 4, so I can't take the square root of 2 and say it's equal to 2. Square root of 2 is just square root of 2, so I got to leave that guy underneath there. So essentially what this means is if I know the length of these two sides here, all I have to do to find the length of the hypotenuse is take one of those sides and multiply it by the square root of 2. So that's legitimately the way that this relationship works. And underneath here, that's kind of all solved for you here too. X root 2 is equal to c. This third side here, basically you just take the length of this side and it's going to give you that third side by multiplying it by the square root of 2. Now, is that interesting to anybody? No. Good. It should not be interesting, but this is what the answer to this actually is. So I want to show you how that looks. Oh, V, why would you lie to us all? So right now, that's the setup. These are both x's. This is x root 2. All you got to do is take whatever this length is, multiply it by root 2. You're good to go. So if I give you a problem that looks like this one, and I give you 17, and I want to finish the other sides here, first off, what's this side going to be? Yeah, 17, because clearly they're opposite the equal angle, so this one's got to be 17. What's the length of this side going to be then? And you could just say RT for root. Yep, this is just 17 root 2. That's the hypotenuse. Super easy. All you got to do, take the length of the side, multiply it by root 2, you've got that third side. And seriously, that's the way that it always works. Now, we call this the easy problem because it really is easy. If you know the length of the leg, you just tack on a root 2 and you're good to go. Now, let's make them a little bit more difficult. First level of difficulty. Oh, hold on. Wait a minute. What have we done? It's actually not that bad. What you do with a problem like this is for a medium-sized one, if they give you the actual hypotenuse, you just have to work backwards. So let's do this. Let's call them x's. If I'm going to work backwards, what I have to remember is that this hypotenuse here is equal to x root 2, right? So if each of these sides is x and I want to solve for them, I'll set up an equation saying that this hypotenuse, this 3 root 8, is equal to that length of the side x times the square root of 2. It's equal to x root 2. Now, here is something that I'm really excited to have you think about for a minute. If I've got a square root of 8 there, can I write that as square root of 2 times something? I want to just, 2 times 4, right? So I can write this 8 as root 8 times root 2. Still got that 3 out there. And whoa. Come on, Bechtel, write your right words. So that's now 4 times 2. So 8 now became 4 times 2. And I've got this as x root 2. All right. I want to show you something real quick. If I want to get rid of that square root of 2, I can totally do it. It's not hard to do. These are just being multiplied. If I divide both sides by that square root of 2, this one will cancel out. And now that I know this one's here, this one will cancel out as well. So what I have left here is I've got x, and this is going to be 3 square root of 4. Now, help me for a second, guys. What's the square root of 4 equal to? It's just 2. So if I can simplify this, then I should. Oh, one more minute. So I'm going to simplify this. This will be 3 times 2, which is x, or x is equal to 6. So that tells me that if I look back up at the top here, each of these is equal to 6. Okay? So I'm going to stop here because we've only got a minute left and I don't want to dig into the 30, 60, 90s yet. That's where we'll start next week. But when you do the homework problems, the second one is actually going to ask you to do a problem with a 30, 60, 90. Don't upload that one unless you really know what to do with that. With these, we've gone through 30s, 45, 45, 90s, and this is the sort of thing that I want you to be able to do. When you go in and do that work, the first one you should totally be able to do is just the Pythagorean theorem. The second one, try the ones that are 45, 45, 90 just to make sure you get some practice. We'll start the beginning of next week talking about 30, 60, 90s, and then we'll roll into what we need to do when we're going to be talking about reviewing for the quiz that you guys are going to have next week. There's not a lot in there about these special right triangles, but I do want you to be aware of them. So do you guys recall, I'm going to stop recording.